In the last video, we disassembled the front half of the hardware. Today we're going to disassemble the back half of it and the power supply. Then see how it distributes the weight. We're going to start by removing the headgear. Because no screws are used to fix the second half, so we infer that it is buckled. We'll use ultrasonic welding to play a fixed role. Look, there's a slit. It uses 8 snaps to hold it in place. And the direction of the buckle is different. These 2 buckles are outward. The other 6 buckles are inward. Then in the mold, the inward buckle needs to shrink the slider inward. The outward buckle needs the outward slider. We can see that there are slider marks here. Look, the slider marks. Can you take a clearer picture this way? The inward slider also has traces left over. There are slight lines on this piece of plastic. We put it next to it. Okay, next we remove the battery part. This is its battery compartment. After removing the head pad, we can see 8 square holes. Tell its model, it's a cross screw. One more. This screw is infused with vinyl. The whole screw is sealed with vinyl. Most likely a disassembly-resistant process. The specification and model of this screw are different from others. Oh well, it turns out he just screwed a black plastic gasket. All 8 screws were unscrewed. We continue to disassemble. There are traces of the pick here. At the bottom of it, we find a knob module that adjusts the tightness. So this module here, it uses a ratchet mechanism. Gear is made of plastic. Structure similar to internal teeth. Then it's like winding up. Limit can be fed back during rotation. Applying lubricating oil can reduce losses caused by friction. That's when the plastics wear off each other. Put it next to it. All that's left is the battery. The battery is divided into left and right parts. This allows for a more balanced weight of the entire hardware. There's a knob in the middle. The knob of the middle square is connected back and forth. The PCB used here is green. It is different from the color used in the previous module. Two colors were used. It doesn't seem very coordinated. Remove this cable. Let's remove the battery module in the middle. It's also a buckle here. We can see some screw holes from the back. This is commonly used in mold design. In order to make the use of the buckle more convenient, she'll leave some holes in advance. Ability to use sliders as little as possible. Designing the snap in the mold is actually very complicated, because the snap involves to molding in the other direction. For example, this part just now, to make this buckle form the shape of a hook. The slider must be used during the demolding process. Slider slides out to the side. To exit this mold, the upper and lower parts of the mold. If we want to directly launch the mold, what should we do? Let me find it. This component. Here we can easily see the hollowed out part. The mold is usually composed of upper and lower parts. If there is demolding in other directions, a slider is required, since the slider will increase the production cost. Therefore, we will minimize the use of sliders in the structural design. The material cost of the mold accounts for about 40% of the total cost. Processing fee, mold design cost, and some special structures. They are all additional costs. And in all the extra costs, the slider is a fixed and easily limited cost. In other words, reduce the use of sliders, and you can clearly see the cost reduction. Then how to control the use of sliders? It's like that. When we hollow at the back of the part, you can avoid using the slider. The significant advantage of hollowing out the back is that it can reduce the cost of molds. At the same time, reduce the use of sliders. It can also accelerate the manufacturing speed of molds in future hardware production. On the one hand, the production cost of the mold is low, the production speed of the mold is fast. On the other hand, when manufacturing products, because the action of sliding the slider is reduced, so the production cycle of the product will be shorter. So here's the piece of hardware in my hand. There's plenty of room for buckles. It is to reduce the slider when forming the buckle. You can hollow it out at the back without using the slider. So, when we saw similar hollowing out on some products, you can guess that it is to reduce the use of sliders, or make room for other structures. These are all methods used to reduce manufacturing costs in mold making. There are also two buckles here. We can now see very clearly. The back of this buckle is a through hole. Therefore, it is easy to draw the conclusion that this buckle must be connected here. Look at this hole. This hole is used to match the buckle. The connection between the whole module and the main body uses two buckles. All around it, we can also see things like positioning ribs used on hardware bodies. Lots of positioning ribs. On the one hand, it can fix the shell. Let me find it. Yes, fix the housing to prevent it from mounting too tightly or loosening too much. Not beyond the edge. Make it look more beautiful. The positioning ribs here allow the product to be assembled downward in the predetermined direction. Instead of swaying from side to side. Since it is not a regular geometric shape, therefore, these positioning ribs play a fixed role. Let these parts be supported. Without these positioning ribs, it's susceptible to deformation. On the other hand, there's still plenty of room for more batteries. Or to make the weight more balanced, or for a more beautiful look. So we can see these positioning tendons. Let's take a look at the gears here. It is linked with the knob of the back cover. Rotate it and we can adjust the tightness of the headband. This is the gear. And then there's the rack. One turn of the gear is almost twice the travel of a rack. And then match the square part here. This way the gears don't slide at will. Listen to the sound of it spinning. We can use it more easily. At the same time, it can also achieve higher mechanical efficiency. But there are still disadvantages to the structure that uses gears. They're not self-locking structures in machinery. Like when it's in motion. When we adjust its tightness with our hands, the gears will also rotate accordingly. The self-locking and self-locking structure is usually realized by the turbine scroll rod. Therefore, many VR glasses products will use it to adjust the pupil distance. Like this one I have. Let me adjust its pupil distance. After adjustment, it needs to be fixed in a certain position. So a turbo bar is used. The other advantage is that it allows for finer adjustment, because it can control the angle of rotation of the turbine by the number of turns of the vortex rod. This allows for self-locking. That is, keep him in a fixed position. As far as possible, the mechanical state should not be changed by external forces. In the case of a non-self-locking structure, its mechanical state is easily changed by external forces. If the gear is used alone, the tightness cannot be controlled. When the two are used together, it can be fixed. Let's have a look at this piece. Yes, that's it. Because plastic is elastic. And when it rotates, it depresses because of its elasticity. And then it jumps. And you can see the limit design on the back. Limit its degree of deformation. The degree of deformation of the material is related to the thickness. Look at these thin tentacles. It will determine how we feel when we use a knob. Change its thickness. When we turn the knob, we get a completely different feeling. We only feel it when it is made. Take a look at this. This metal piece is a spring. It is usually used to fix a rotating part to another part. A spring will definitely be used on the shaft of the watch. It prevents the entire part from being pulled out. Here is a groove. Then insert the clasp from the side. The clasp generates shear force at a radial angle. So we couldn't get it out, unless you break it or use specialized tools. Special tools are required to remove or install the spring. I don't have that kind of tool right now. It was too hard and I gave up. Let's continue. I see a piece of tape here. The battery is glued to the structural part by double-sided tape. And that structure is held in place by another structure. This is the harness. There's a piece of metal between the harness and the structure. Maybe for heat dissipation or signal transmission. The welding of batteries and PCBs uses nickel metal hydride sheets. The back of the nickel hydride sheet is protected with black tape. The red one might be a temperature sensor to detect the temperature of the battery. I used a whole piece of adhesive to stick the battery. On the back is a flat piece of plastic. It will be very difficult to disassemble. Two smooth surfaces bonded together. It is not only the bonding of glue, but also the negative pressure caused by vacuum. How is this PCB fixed? The batteries on both sides have been removed. It is also pasted with double-sided tape. The battery and PCB are pasted with double-sided tape. Compared with the previous module, the process is very different. Maybe it was done by two different teams. Look at this structure. This structure has a glossy facade on the front. It's not polished, it's an ordinary glossy surface. It is simple polishing after processing. It wasn't finely polished. The back is the same. The traces of the thimble here have added texture, possibly for better exhaust. On the other hand, there are no signs of stress when the top touches. The thickness of the structural parts is approximately between 1.2 mm and 1.5 mm, not very thick. Let me find what it's made of. Yes, PC and ABS VO, this is it. There's a little string of characters underneath it. This string of small characters is a mandatory standard for export trade and must be marked on the material. Types of labeling materials. Show PCs and ABS. VO indicates its fire rating because it's attached to the battery. The flame retardant grade should be VO. This part, we can see two obvious inlets. These two are the glue inlets. Here is a logo. I guess it is achieved by the process of pad printing, because the paint of this logo is very thin. That's what pad printing is characterized by, very thin paint. And look at this. Now we can visualize the component. It probably uses a gluing process. It may be two-color injection molding. It may also be glued. Because there is some glue overflow on the bonding surface of the two layers of glue, you can see two layers. In the process of gluing, bury the cable in advance, then cover it with a layer of soft glue. Okay, see you in the next video.